Hello, welcome to video 5 in our lecture Advanced Mathematic Modeling. In the last video I showed you the conditional probability, so how can we calculate the probability of an event given that some other event happened. And in this lecture now I want to show you a very important application of the conditional probability, and that is the Bayes rule or Bayes theory, how it's often called. So what do we mean by this? So very often we are looking for the conditional probability of an event A given another event B, but what we know is just the reverse conditional probability, the probability B given A and probability B given the complement of A. So is there a way given these to calculate the reverse conditional probability? There's many applications of this question in the modeling context. A typical example is that A corresponds to our model parameters and B corresponds to the results of an experiment. And so what we would like to know is what is the probability that the parameters that we used in our model, that these parameters fit the experiment. But what we know is the reverse thing, what we can show by simulations using some parameters, how good do these parameters fit the experiments. So is there a way from this to go to this? And to calculate this is actually quite simple. So we want to calculate the probability of A given B. So we use our definition, the probability of the intersection divided by probability of B. And the intersection we decompose here as the conditional probability B given A times the probability of A. And here you see the magic has already happened, because here was the probability A given B, and suddenly here we have the probability B given A. Then we have also still to deal with the denominator, and here we can use the partition rule. So we say, okay, probability B is the conditional probability B given A times P of A plus the conditional probability B given the complement of A times the probability of the complement. So we have this expression here, and this expression has just the reverted conditional probabilities, and calculating this we're able to calculate the conditional probability A given B. So when it's expressed like this here, it's just a simple arithmetic to calculate this, but this actually is the starting point for the whole framework of statistical inference with the Bayes rule. I want now to show you two examples how we can make use of this. The first example is very famous. That's the false positives. Let's assume there's a rare disease, and this recently was becoming popular again with the coronavirus, with COVID-19. Yeah, so that's still a rare disease, for example, in Germany. Or and we have a test for this disease, and this test might have a wrong outcome. Or we could have pregnancy, and the question is, we have a pregnancy test. And now, let's say we have this, how many people have this rare disease? Let's assume we have one person on average has this disease, 110 to 500,000 people. One of 100,000 people has the disease on average. Now we have a test, and now the test is not 100% correct as all tests, and the test shows positive. With the probability P equals 99 over 100. So we have a 99% chance that the test is positive if the person is sick. Yeah, so then the test is okay. But sometimes, so with 1%, the test shows positive even though the person is healthy. That's the question on corona with this antigen tests here. So a person might have corona or might not have corona, and with the small likelihood we have this false positive that the test indicates that the person is positive with corona, even though in fact the person is healthy. Or with a pregnancy test here, so the test shows positive even though the woman is not pregnant. So and now the question is, assume the test shows positive, what is the likelihood to be sick? Test is positive, what is the chance to be really sick? Or the pregnancy test is positive, what's the likelihood that the woman is really pregnant? And usually one would assume, okay, if the pregnancy test is positive, I should be very sure that I'm pregnant. Or the corona test is positive, then we should be very sure that the person is sick. But let's calculate this with the Bayes theorem. So what does this mean? So you see we ask here for conditional probability. So we ask for the probability to be sick given that the test is positive. And now we apply Bayes theorem. So that is equal to the probability to be that have a positive test if the person is sick times the probability to be sick divided by probability for positive test to be sick times the probability to be sick plus the probability to have positive test even though the person is healthy times the probability to be healthy. So I hope you still can read my writing here. So now we can calculate this. So the probability to have a positive test if a person is sick, it's 90 over 100, 99 over 100. The probability to be sick is 1 in 10 to 5, so it's 10 to minus 5. And this we have to divide here first with the same thing again. 99 over 100 times 10 to minus 5 plus the probability the test is positive even though the person is healthy. That's 1 over 100, and the probability to be healthy is 1 minus the probability to be sick. And now we can multiply everything by 100, and then we have here 99. So we multiply also by 10 to the power 5, and we have here also 99, and then we have 10 to can you think about? Yeah, we have here 5, and then 1 minus 10 to minus 5, that's about 1. And when you calculate this, we have something like 1 over 1000, so it's a small number. That means the probability to really be sick, even though you have a positive test, is very small. And of course, this whole argument depends that the probabilities are really like this, so that we really have a rare disease, yeah, only then this works out. But this simple example of the false positives shows really the questions, the whole testing of a rare disease if the test has a small chance to be wrong. So that's one very famous example of this Bayes theorem. I want to give you another example, maybe in the context of here a lecture. So let's assume I want to make a written exercise and give you a multiple choice test. And let's say you have a number of C different choices. Where you can make your cross. And let's assume the student knows the correct answer with probability P. And now what I as a lecturer want to know, given the answer is correct, what is the likelihood that the students really knew the answer? And so let's write some to calculate this. Let's introduce some notation. Say call A, the answer is correct. So the cross is in the correct position. Let's call S, that the student knows the correct answer. And so we can already say P of S equals P, because that was our assumption, and the probability that the student doesn't know the answer equals 1 minus P. And now we can use our partition rule. So the probability that the answer is correct is the probability we have a correct answer given the student knows the correct answer, plus the conditional probability the answer is correct even the student didn't know the correct answer and was just lucky. So, and so now how do we calculate this? And then we can say, of course, the conditional probability that the answer is correct when the student knew the answer is 1. Yeah. And this here is P, so here we just have P. And then now we have to say what's the chance that the student gives the correct answer even though he didn't know the answer. That depends on the number of choices, so it should be 1 over the number of possible choices, and then multiplied with the probability that the student didn't know the answer. So here we have the probability to have a correct answer. Now we use the Bayes trick. So we say the probability that the student knew the correct answer given that he gave a correct answer. So that's what I was interested. So now that's the probability of A given S times the probability of S divided by probability of A. This was this partition thing, but I calculated this already. This here we calculated also already, that's P divided 1 plus 1 over C times 1 minus P. So that's now the solution to our answer. So the probability that the student gives a correct, that he knew the answer given he has a correct answer is this formula. But typically we are not, that's not enough. Now we should, and that's also, this goes also for all the rest of exercises. When you do this, we want of course to analyze this to get an idea or visualization of this. So how can we do this? Maybe first we rewrite this a little bit. So we can rewrite this as if we multiply by C, and we have here Cp over 1 plus C minus 1 P, but that's just a rewriting of the whole thing. Yeah, or maybe I should have written this in this form. Maybe say here this is C over C plus 1 minus P over P. And now what I want to know as a, in my design of my exercise, how many choices should I give to the student? Oh, there, Jesus. Sorry, sometimes I forget to move the paper here. So C over C plus 1 minus P over P. And so my variable, that's what I can control, is the number of choices. So I now want to make a graph. So I want to graph this. So that's C, my number of choices. And what I want to know is this conditional probability that the student really knew the answer when he gives the correct answer. And so what you can see, this is a saturating function. This goes to 1 when C is very large. And we have a half saturation constant when C equals (1 minus P over P). And now the question is, I want a certain level of certainty that if the student gave a correct answer that he really knew it, and then I can see from this line how many answers should I allow. Now it depends a bit here on my assumption about the knowledge of the student, so we can make another graph. Now I have here the probability P that the student knows the correct answer, which is between 0 and 1. And here we have our C1/2, C1/2, this half saturation value. And so you see that's a function which goes to 0 when p=1, it's 0. And for example, when we give here 0.1, we have here 9. So it's a function which decays like this. So this means if, for example, p equals 0.1, if I think that the student knows the correct answer is 10%, then with a number of 9 questions, we have here 50% probability. And so you see here with the Bayes theorem, we can get some idea how many questions we would have to put in a multiple choice test. So just that's another nice example to see how you can apply this Bayes theorem to calculate conditional probabilities. So that's most of the first lectures where I gave you some introduction, some primer about probability theory. That's all things we might need later for the lecture. And what we will continue is then to not have arbitrary events, not just arbitrary sets, but we will want to go to numbers, and so we will introduce random numbers that we can really compare different outcomes of an experiment. But this will be in the next lectures. For the moment, thank you.